Okay, thank you very much. Good morning, everyone. So the plan is first discuss a bit why the theoretical modeling of gravitational waveforms is crucial for all the measurements, for at least for binary systems. And then, as we all know, detectors are improving in sensitivity, and new instruments are being planned. So there are exciting prospects for testing GR and black holes, but concurrently, this also requires improving the theoretical models. And in particular, if we want to also test for deviations from GR, that has long been an important problem. So people have given a lot of thought how to test it in a meaningful way. But we also need to have some examples of what waveforms in theories beyond GR could look like, what could be generic phenomena we can look for. And I will illustrate this a bit, and also the methodology in a case study focusing on higher curvature theories of gravity coupled with a dynamical scalar field, where black holes can have scalar hair, which modifies the dynamics, and you can also get scalar tidal effects. So I will come back to a bit of the material you discussed on Tuesday about tidal love numbers. And then discuss sort of what interesting features arise in the gravitational waves and what is to come in the future. And the main references are the two papers colored in blue here. The credit for the work goes to amazing PhD students, Banafsheh Shiralilu, Iris van Gemeren, and Gaston Cressy. And we are also in all cases not the first one to work on these problems. We've just added a bit more information and advanced the field. So I also give you a few references of earlier and follow-up work, but if you really want all the references, please check the papers. So let's start first of all by recalling the general features of a waveform from binary inspirals and mergers and beyond. So, well, you've probably all seen the shape of the waveform, which is for a binary system with nearly equal masses on circular orbits and spins aligned with the orbital angular momentum. And the detailed features of the gravitational waves depend on all the source physics. And in particular, for the inspiral part, the gravitational waves are very sensitive to the time evolution of the phase. And that encodes a lot of information about the source, which is not so easily visible, because we have to remember, even though the waveform looks relatively simple shape, but in reality, it really reflects the dynamical space-time of a binary system. And there's a very nonlinear relationship between asymptotic waves that we measure in the detectors and the fundamental source properties. And the way the signal detection and interpretation, all the measurements work, is by cross-correlating theoretical models that provide the link between the waveforms and the source physics with the data, and then determine the most likely distribution of source parameters. So really, if the theoretical models are off, then all our measurements are biased, essentially. So it is important to advance the theoretical modeling, but this is actually a very difficult problem. So you might have talked about gravitational waves from the ring down also, which is kind of a simpler setup, because you just have one perturbed object and you can extract the gravitational waves. At least at late times, it's a perturbed object. But for the inspiral part, you have a dynamical space-time of a two-body system for which we don't have an exact solution that we can do perturbation theory to. But there are some regimes where there's a clear hierarchy of scales which we can exploit to make some analytical approximations. And unfortunately, it's not possible to have one approximation for the entire space-time. We have to really look at different patches of the space-time and make different approximations in each. And then the key role of the modeling is also to connect the information between the different regimes. So for example, we have the strong field regions near each black hole, which we have to treat in fully non-perturbative relativistic theory. But then on the orbital scale, the objects are very far separated. So the size of the orbit is much larger than the size of the objects. So basically for the regions near the objects, we use black hole perturbation theory. Then at the orbital scale, for the orbital dynamics, we have post-Newtonian expansions, which assume small gravitational interaction and weak small velocities for a gravitationally bound system. So the two are nearly equal. And we make the small size expansion as an independent expansion. And then finally, near null infinity, we do post-Minkowski expansions where space-time is nearly flat with some perturbations, which are the gravitational waves. Now, in GR, these methods have been developed over, it took many decades to really sort out all the subtleties of how to do it and make the connection between all these regimes in a mathematically rigorous way. But we also, of course, want to go beyond GR because we don't think GR is the ultimate theory of gravity. So we want to know, can gravitational waves at these scales accessible to them test for some signatures of deviations? And what is mostly done is to try to, since we don't know what is an ultimate theory and what could be its low energy manifestations, what is currently mostly done is parameterized model agnostic tests, which means one takes a GR waveform and by hand simply adds small deformations to it and then constrains the deformation parameters or multiple of them. But of course, it is also clear that we would like to have some examples of what a full waveform could look like in GR to, well, test the robustness of these parameterized tests and maybe get more stringent constraints and for also understand possible new phenomena that we should look for with these parameterized deviations. So of course, when you say going beyond GR, there's a plethora of options. You can go in different directions, add extra fields, higher derivatives, extra dimensions, non-locality, and so on. So, of course, we don't want to spend all our time computing in each different theory. So, as a first step, we made one choice of a class of theories, which is called Einstein scalar Gauss-Bonnet gravity. And basically, it has it reduces to GR in the small coupling limit or at low curvatures. But then there's an extra scalar field that is coupled to the Gauss-Bonnet curvature invariant. So it's a kind of quadratic in curvature correction, but through this special topological term. And it's a family of theories. So for different coupling functions, you can get different behaviors. So it has, yeah, some motivations. Also, because you can show that the equations of motion are still second order, even though you have this quadratic order curvature invariant, people can actually do numerical relativity simulations. So it's a good way to also connect between analytical and numerical relativity. So these are kind of the motivations why we chose to look at this example. So what are now the consequences for black holes in this class of theory? Well, it turns out it is common for black holes to have scalar hair. So you can evade the kind of new no-hair theorem proposed by Bekenstein in 1995 for many cases, depending, of course, on the choice of coupling function you make and also the choice of black hole you try to consider. And yeah, there are some general conditions under which you get scalar hair on black holes, which are, if you want to read all about it, there was a recent review article on the archive written about all about the scalarization mechanism. But so we will now assume there is such a scalarized solution, and asymptotically, this scalar condensate around the black hole behaves like a scalar charge, which is called D here, as a 1/r fall off behavior. And this, we call it a scalar charge, but is not an independent quantity. Once you have fixed all the parameters in your theory and the properties of the black hole, then it is completely determined in terms of them. For example, if you assume the small coupling limit where you say these higher curvature corrections are small, then you can get it explicitly in terms of the coupling coefficient, the derivative of the coupling function, and the horizon radius of the black hole. Now, we are interested in putting such a scalarized black hole in a binary system and kind of adapting the general methods I discussed before to this particular case. So now we have the black hole still has the Schwarzschild radius as its characteristic scale in the small coupling approximation. But then we also have the scale of the scalar condensate around it, which is, of course, since we are considering here a massless scalar field, this falls off quite slowly. So one might worry, well, our approximation might not work so well for a binary system. But it turns out when we look at the exact profile of the scalar condensate, there's still kind of a characteristic scale we can associate to it where about 90% of the energy in the field is concentrated. And that is within a few Schwarzschild radii from the black hole. So this we take kind of as our characteristic size of the matter distribution, which we assume is smaller than the orbital separation. And then we set up a triple perturbative expansion for the orbital dynamics in terms of the post-Newtonian corrections, this higher curvature corrections parameterizing the deviations from GR, and the finite size effects. And yeah, in each we go to leading order, except for the post-Newtonian corrections, we go to one post-Newtonian order. And then to describe the binary on the orbital scale, a typical approach that is adopted is that the two black holes and their scalar condensates are reduced to just some center of mass world lines plus a bunch of multipole moments that describe all their effects of their internal structure or possible spins, which we neglect, however, here. So we have an effective action for the orbital dynamics given by the gravitational action plus the world line actions of the two particles, which are scalar dependent masses, and then possible finite size effects. And it turns out in this case, the dominant finite size effects are due to tidal interactions of scalar dipoles. So the idea is that when the two scalar condensates are in a binary system, they produce a scalar gradient across the other's matter distribution. So in response to that, the scalar condensates deform and develop an induced dipole moment, and of course also higher moments, but the dipole is the dominant effect. And so then we work in the adiabatic limit, where we assume that the characteristic frequencies associated to this scalar condensate, which in the small coupling limit are of order the Schwarzschild quasi-normal mode frequency, that those frequencies are much higher than the orbital tidal forcing frequency during the inspiral, at least the portion we are considering. And in that case, we define tidal deformability or love number as the ratio of the induced scalar tidal moment divided by the dipolar scalar tidal field. And this now gives us a description on the orbital scale, but it is still dependent on some parameters like the masses and the this tidal deformability parameter lambda s, which at this stage are just coupling coefficients in this effective theory. So now the key is, how do we connect this to the fundamental properties of the black holes and scalar condensates? And this is a bit of a subtle issue because we're dealing with nonlinear gravitational effects. And yeah, of course, here also scalar effects. So there have been a lot of concerns in the literature about how do we connect, especially this tidal deformability lambda parameter or tidal love number to the fundamental properties of the black hole. And is the property of the black hole that we compute and call the tidal love number indeed the parameter that we ultimately measure in gravitational waves? And this is not a priori so clear. So one useful theoretical tool is to use analytic continuation, because it turns out in 4 space-time dimensions and for integer multiple moments, tidal effects can become degenerate with post-Newtonian corrections. But as soon as you go to higher dimensions or do this analytic continuation in either dimensions or multiple, you see that they are clearly separate. It's just in 4 space-time dimensions there happens to be some degeneracy. And then based on this, we can actually say, well, if we try to match from the orbital scale to the scale of the objects, that's still kind of a nonlinear regime, and we're potentially impacted by some nonlinearities or coordinate choices or so. So instead we can do the matching at null infinity, where space-time is Minkowski, and we can work with invariant scattering amplitudes there, also using double null coordinates, which have a geometric meaning. So we kind of try to eliminate as many possible subtleties as we can. And in this case, scattering just means, instead of considering how does an object respond to a stationary perturbation, we ask how does it respond to a wave-like perturbation, and then we extract the amplitudes of the in and outgoing waves at null infinity and make the identification with the effective theory there. So it's quite similar as the usual methods, but working just with in and outgoing wave bases. So it's not a quantum mechanical scattering in that sense. It's really a classical scattering, just using the different basis states. So the idea is illustrated again here. You want to compute for a black hole in your full theory these in and outgoing scattering amplitudes, and in particular you want to know how they behave near null infinity, and match near null infinity to the effective description, where you also have some scattering amplitudes, which then determine the parameters of these world line skeletons, where the multiple moments can now be generalized to be frequency dependent responses to the tidal field. So that in the limit of 0 frequency, it again reduces to the tidal love numbers. But even in this scattering approximation or setup, one naturally gets the full frequency dependent response out of it. So that's also quite nice. And yes.
Where did the go to? So suppose I take ground and I do the coordinate to that regular coordinate.
Yes.
In this.
Yes, in this setup, you are working at null infinity, where space-time is the Minkowski space-time, and you would use the double null coordinates determined by the characteristic directions.
Well, it's still
so
they fall off differently. So I guess when you do these coordinates, you do have some ambiguity.
No, because you're not looking at a stationary space-time and read of the multiple moments in terms of coefficients of the fall-off, but instead you really look at the amplitudes of the in and outgoing waves, which are at null infinity are some gauge invariant quantities. So that is kind of the difference. Okay, Vitor is happy, so we can continue. So when you work this out, let's say we first consider a non-scalarized black hole to understand what happens to the black hole, and then later on we will add the scalar condensate. So then you can work out in your effective world line theory how the response function depends on these scattering amplitudes. And okay, you get some functional dependence, but you see it clearly the response function lambda depends on this ratio of in and outgoing wave amplitudes at infinity. And then the next step is to match to the ones computed in the full theory. And it turns out to leading order, they get identified, but this is also quite some subtlety, and yeah, for numerical evaluations, one might need to be a bit careful. But it turns out then, if you want to see, does this relation now make sense in terms of what we know about love numbers of black holes? So we take the zero frequency limit and specialize now to 4 space-time dimensions. And we find indeed the real part of this response function is 0. So the tidal love numbers vanish here for the scalar case. And for the imaginary part at low frequencies of the love number, we get exactly the absorption cross-section as we would also expect. So this is for a non-scalarized black hole. But now if we have the scalar condensate, that of course changes things, because the scalar condensate indeed responds to a scalar perturbation with a non-zero scalar love number, which can now be computed and turns out to be also determined in terms of the coupling parameter, and now the second derivative of the coupling function. And this is also, I mean, again, I want to emphasize we're not the first ones to advocate these effects. These have been known in scalar tensor theories for a long time, since Damour and Esposito-Farès in 1994, recently revisited by Laura Bernard. But here we have them for black holes, which is kind of a cleaner system, where, because we know for the non-scalarized black hole, they're 0. So now when it's scalarized, they're non-zero if the coupling function has a non-vanishing second derivative. Okay, so then how do we then apply all of this? Well, we apply these approximations, which, yeah, it's a lot of algebra and carefully keeping track of all the perturbative expansions in the 3 different approximations. Then if we specialize to circular orbits and compute, for example, the gauge invariant binding energy as a function of frequency, we can get what are the corrections now. Well, there's first of all a correction due to just the scalar corrections themselves, which is this ES, which is similar in functional form as in other theories with scalar fields, for example, scalar tensor gravity, except the parameters that characterize the world line skeletons are related in a different way to the properties of the black holes. And then we see the tidal and higher curvature corrections come in with the same scaling in the frequency. Now, the next step is to compute the radiation. And there are also scalar waves produced by the fact that they are orbiting scalar monopoles from just the scalarized black holes, but then also these tidally induced dipole moments contribute directly to the scalar radiation. And there's also gravitational waves, of course. Now the scalar radiation scales as x to the 4, where x is a frequency parameter, whereas the tensor waves scale as x to the 5. So they are higher powers of the frequency. So there is usually a regime early on in the inspiral where the evolution of the system is dominated by the scalar energy losses. Yes. Well, I did not say anything yet about the scales. I said, okay, for the Gauss-Bonnet, we have currently constraints on this coupling coefficient alpha. It's of order 1 kilometer squared. So I would not put something huge there. Of course, the current constraints are also dependent on current models, which have shortcomings. But then I said here, well, I say a characteristic scale for the scalar condensate is where about 90% of its energy is concentrated. So far, these are the only scales I've assumed. And I've said that the orbital separation is larger than a few of these Schwarzschild radii. So far, no numbers have been put in. It's all still quite generic in terms of general coupling functions, except we make the approximation here that alpha divided by the Schwarzschild radius squared is smaller than 1. So that we can make a perturbative approximation in it. There are many RS is something that. Yes, if you, yeah, that's true.
alpha you was fixed or something that if the phenomenological parameter that you check it needs given?
Yes, alpha is a parameter to be constrained by observations.
That was, yeah, for every time. Typically, when we think about alpha,
Yes.
some fundamental fixed quantity, but probably you don't want to think about it.
Yes, I mean, if you tell me from string theory alpha has to be this value, then we can plug it in. Yes.
There is no way that you can.
Yes. So the philosophy here is more, well, there's a lot of unexplored territory between current scales and the Planck scale. So let's look for something. And okay, we chose this model, but it's also meant as kind of a proxy to give some intuition about phenomenology. So, okay, you're also happy now. Okay. Yeah.
Is a breath compared to this charge. The one in circle. Are they the same one?
No. You mean the tidal corrections to this scalar radiation?
Right.
Yes.
The leading order is charge.
Yes.
Use that.
Yes. Yes. That's true. Yeah.
I also have a question.
Yeah.
The dipole radiation is suppressed in the equal mass.
Yes.
Things, right? So that there's there are coefficients there.
Yes, yes. I'm just not showing them because yeah, it's true for the case of exactly equal masses. This dipole radiation is at least at leading or it's 0. But then there are also higher order scalar fluxes that also come in. And it's okay, exactly identical black holes is also quite a contrived situation. So yeah, I'm excluding this case from the considerations. Any more questions before I go on? Okay, perfect. So now, yes, we've understood qualitatively that, okay, the energetics of the system gets modified and now the radiation gets modified. Then we can compute the gravitational waves and in particular the phase evolution of the system. And we compute this by saying, well, the power radiated in gravitational waves, which are these related to these fluxes I showed here, that has to be balanced by a change in energy of the system, which goes back to the energy I showed here. So that leads to a frequency evolution and hence an inspiral. And interestingly, then when we analyze how do effects in the early inspiral, so when the scalar flux dominates the losses, compared to the late inspiral, we see very different dependencies on parameters. So what is shown in the plot here is the accumulated phase difference from GR for different mass ratios. So the solid lines are the ones that are closest to the equal masses, and the dotted lines are the ones with the most unequal masses. And you see clearly in the early inspiral, the trends are exactly opposite compared to the late inspiral with respect to the mass ratio. And the question is, well, now we have several effects, the pure scalar charges, the induced scalar dipoles due to tidal effects and the higher curvature corrections. So which ones are responsible for these parameter dependencies? And in particular, I said the tidal and Gauss-Bonnet corrections, at least in the binding energy, scale similarly. So we want to understand, which of these is responsible. And here, what is shown is again the accumulated phase difference due to only tidal and Gauss-Bonnet effects, where the tidal effects are in the solid lines and the Gauss-Bonnet higher curvature effects are the dashed lines. And you should look probably at the inset, which focuses on small couplings, which is kind of within our approximations. And you see very quickly in the early inspiral, after aligning the phases, we see that there's a relatively quick accumulation of phase difference due to these induced tidal effects. Whereas in the late inspiral, the tidal effects are relatively small. And on the other hand, the higher curvature effects, there's not so much difference between their relative importance between the late and early inspiral. So that's already interesting. And also yes?
You expect this because when black holes are far away, but the curvature is smaller.
Yes.
So you could expect this, and you could also expect that curvature becomes important when they become closer.
Yes, that's true. And yeah, that's a good sanity check. It's just we wanted to understand, because if we look at all the contributions together and we look at the early versus late inspiral, we see these very different parameter dependencies. So we wanted to understand where it comes from. And yes, as you said, it's not unexpected that the higher curvature effects, become important in the late inspiral. But more interestingly was the scaling of the tidal effects with the coupling. So yeah, that was interesting. And of course, these different parameter dependencies also open up interesting prospects for observing, for example, the early inspiral with LISA, and then some weeks later observing the late inspiral and merger with ground-based detectors. So this is shown here for some of the example cases I showed. For example, the 18 solar mass case was one of the examples I showed here. Was exactly this example case. And yeah, of course, it depends what distance they are at, but at a distance of 150 megaparsec, we can still see both the early inspiral and the late inspiral. And the vertical lines here kind of indicate where the transition between what I call the early inspiral and the late inspiral occurs in frequency. So this is simply estimated by saying the scalar flux has to be equal to the tensor flux. And that gives the vertical dashed lines for the parameter choices here. Of course, all of this I'm showing depends on what parameters one chooses, but these are some illustrative examples. Now, of course, we don't expect this transition to be exactly sharp, where the phase transitions from the scalar-driven to the tensor-driven evolution. So we also tried to estimate numerically how big is this transition regime. And actually, it turns out it's quite a lot bigger than one might expect. So you see this illustrated here, where the solid black line is the full numerical solution to the energy balance equation. And then these dotted and dashed lines are the respective approximations for the early inspiral in the dashed line and the late inspiral in the dotted line. And you see here the scale of this frequency transition regime is quite large, where neither approximation is so good. So one has to be a bit careful in applying the different formulas for the phase evolution. Or of course, if one works in the time domain, this problem with having different expressions for the early and late inspiral is avoided. So that's also a resolution.
So how good is the approximation that you're far away from the scale of the from the hair? So you're using an approximation.
Yes. Yes.
How good is the approximation when you transition from that or without the
You mean is what I call the L phi still smaller than the orbital separation?
Yeah, much smaller.
Yeah. So I don't have the numbers here, but yeah, for example, okay, I mean, these black holes are kind of similar to black holes that have been observed with LIGO. Yes. So and there they were already separated at, you know, I don't know how many, but dozens of Schwarzschild radii before they merged. And I'm saying this L phi, okay, there's no clear boundary, of course, for it. But if we say 90% of the energy of the scalar field, then it is a few Schwarzschild radii. And the transition occurs way before this LIGO band. So I don't have the exact numbers, but yeah. So of course it is a concern that L phi could.
Yeah, we saw just for the we saw a very sensitive dependence. You were doing it as well as
Yeah.
a very sensitive dependence on where exactly.
Yeah, okay, that's maybe something to be careful of. But anyway, now we are also working on including a mass for the scalar field, because it seems having a completely massless field is really unrealistic, and including a mass changes a lot of things about the hair and so on. So then this L phi we also expect to become more concentrated and fall off more rapidly than. So yeah, that will probably be a more realistic case. But yeah, you're right. Here it is, of course, a concern that our approximations are not that good, maybe. But still, it gives some idea of what could happen, and what also to be careful about if you see one of these multi-band sources, you have to know that there could be different parameter dependencies in the early and late inspiral, which can benefit you, of course, to disentangle degeneracies, but also if you don't know that, you might not identify the two as one source or something like this. So, okay. Yes, so this side of the transition regime is also a caveat. So in summary, then, okay, I'm wrapping up anyway. Yes, yes, okay. Yeah, so basically in this talk, I tried to convince you that we also want to have some examples of gravitational waveforms in classes of theories beyond GR, and especially try to identify general features that we can look for that are not specific to a single theory. But of course, to identify those, we do some case studies. And I've also used this kind of to motivate a bit the general methodology of how much work it takes to compute waveforms going from fundamental properties of the objects to the final waveform that is observed in the detectors, at least for the inspiral part. And so I've mainly focused on black holes with scalar hair and talked about the scalar tidal effects in the approximation of that the dipole tidal effects dominate, and the adiabatic limit where we have just a constant tidal love number, neglecting any internal time scale of the scalar condensates. And yeah, so we talked a little bit about the different imprints due to the tidal and higher curvature effects. And also I motivated that to avoid some ambiguities in relating between love numbers of perturbed objects to gravitational wave imprints, it's useful to consider scattering calculations, because you can do them at null infinity and avoid several gauge dependent subtleties. And in summary, of course, there's an exciting future ahead with gravitational waves, but there's also a lot more to be done to develop the theoretical tools and gravitational waveform models. So thank you very much.
Other questions or remarks?
I don't know almost anything about scalar Gauss-Bonnet theory. So, but the question I was asking is, you have a scalar, you haven't detected any scalar. So the scalar has to be coupled only gravitationally to the matter. This scalar could be dark matter. So you could put some constraint, also an observation of a black hole which is near the core of a galaxy, and a black hole which is far away from the core.
Yes.
Does it make any sense? I mean,
yes. So of course, yes. So scalar fields are also proposed as dark matter candidates, or at least ultralight bosons also. And of course, it's also interesting to ask: can we distinguish between a scalar field in this kind of modified gravity theory from just an extra scalar field that forms a super radiant cloud around a black hole, or some other dark matter mini spike also? Yes. So I've not seen specific studies of exactly this scalar field in this particular theory as a dark matter candidate. I've seen this theory also used to explain dark energy. But yeah, that could be a possible future direction, I guess.
Okay.
Yeah.
Question, please.
Yes. Yeah.
Would not it be better seen in the polarization of the GW? Because if you have more than two modes, I mean, which is propagating, then would not it have significant effects there?
I don't think in this case you see so much of the breathing mode or anything, but I'm not sure about this. Yeah. Yeah. Yeah.
Other question is, you were talking going to null infinity to, define this amplitude ratio and other things, right?
Yeah.
But normally when we talk about this tidal fields, there are these some objects which are moving.
Yes.
And when
Yeah.
really do not go to infinity.
Yes.
So in your scattering context, how can you use the fact that at infinity it is Gauss-Bonnet?
Yes, that's a very good question. So the problem is when you use this intermediate range between the compact object and the orbital scale to match, then it's still kind of in the strong field region. Non-linearities can be a problem and so on. And you work with kind of, coordinate, you kind of read off a fall of the space-time of the object, which you can modify by coordinate transformations, or you might not be able to disentangle a decaying from a growing solution. So because we are saying, okay, if you do analytic continuation in dimensions or multiple order, you clearly see that these tidal effects and post-Newtonian corrections, for example, separate distinctly. And so you might as well, because you're interested in matching coefficients in an effective action description to the fundamental properties. So to match these coefficients, then you might as well do it via a different method, not considering this matching in the intermediate, but instead doing it in a scattering scenario. Because all you want to do is match the coefficients in the effective action to fundamental properties.
Just ask one more. So the point is, I mean, in this approach, when you do it in the intermediate regime, it does not depend on asymptotic properties. But in your case, suppose I'm doing it in asymptotic de Sitter spacetime, I think your tidal love number will change, right? So
probably.
So then there would be a two distinct love number from two different methods. So how to reconcile the two?
Okay, so you're saying now.
So I'm saying that if I use the intermediate region, the fall off and growing mode solutions, there is no relation to the asymptotic symmetries of the space-time. It just relates to an intermediate region. But if I use the scattering method, you had to assume the asymptotic is Minkowski. But suppose it is not, it is de Sitter. Then I would suppose that your result will be modified due to that.
Well, in a sense, then you have to set up an effective field theory of this effective world line description, the appropriate infinity of where the wave scattering amplitudes can be extracted. So yes, the result I showed here of how the love number depends on these scattering amplitudes will probably be modified because you have to modify also the effective field theory description. Yes, that is definitely true. Yeah, good point.
Thank you.
Okay, I have a general question. So you said experiments and theoretical modeling go hand in hand.
Yes.
And so on one hand, it's important to model the possible signal from deviation from general relativity. On the other hand, you said there are very many models, and so you have to choose one and maybe identify some universal properties shared by more classes. The question is whether one could be in a situation where there is the real signal, so it doesn't fit any model. Yeah, and whether one could have a blind search, or whether one should necessarily use some theoretical template model.
Yes. So these, what you say, these kind of blind searches for general inconsistencies with GR.
Yes, the worst scenario, say whether we could mix some deviation from general relativity just because we don't have nobody figure out the right model yet.
Yes, but this is currently already being done. To just be completely agnostic and ask, does a deviation from GR, can we constrain it, or can we look for consistencies between inspiral and ring down, or yeah, these kind of parameterized tests are being done. Also measuring the tensor tidal love number that you discussed on Tuesday is another kind of very generic test. So this is already being done, but I'm arguing that in addition to these kinds of tests, which, because you really don't know, you're also not so sensitive to deviations. So you would like to have some examples of waveforms. So in a theory that is not GR, to get some intuition about what deviations you should look for, because it's not just a single deformation parameter, it's all deformations kind of in a certain, all connected together in a certain.
Okay.
And also to test, are your parameterized pipelines good at picking up these signals or not? So this was the idea.
I see.
So I was wondering about the importance of the tidal dipole. Is it obvious that if the dephasing is larger than other terms, when you do a parameter estimation, that will still be a dominant term? Because, for example, I was thinking, in order to constrain this alpha the most, you want light black holes, but then you don't know whether they are black holes or neutron stars, and then you will also have a tidal effect when you do parameter estimation, because you have to include a tidal off number, and maybe that could spoil the measurability of the dipole.
Yeah.
Is it possible?
Yes, that's true. I mean, in this theory, neutron stars don't scalarize in the same way as black holes, unless they're extremely massive and compact.
No, I was thinking about parameter estimation point of view, because you don't know whether that is a black hole, say, of this theory, or a neutron star in GR.
Oh yes, but then the dipole effect scales differently with frequency than the GR tensor tidal effect.
And that should not spoil parameter estimation.
Well, yeah, but probably if it still does, because it's not so clearly separated, but with a sufficiently loud signal, you should be able to distinguish. But I agree that this is also a problem to be looked at.
So Tanja, going back to the extension of this hair.
Yeah.
Do you include dynamical friction here in some form?
No.
And what is the relative importance of that? Do you have any estimate?
No, we did not estimate the density of the hair at extremely high distances. Yeah, we just said, well, most of the energy is not concentrated out at large distances. But yeah, it's another shortcoming of the model.
If not, we thank Tanja again. Okay, we have a break and we will